In our last unit, I had several students say that they liked that I made a video of me doing the problems on the last worksheet of the unit. So I thought I would do that again for this unit. I'm going to split this up into 2 videos. Okay, I'll probably do the first 2 pages and then the last 2 pages. All right, number 1. The function p models the population of rabbits on a farm and is given by this function for time greater than 0. So they give me this function, where t is measured in months since the start of the year. Which of the following describes the population of the rabbits as time increases? That's a key phrase there. As time increases, what is going to happen to the population of the rabbits? So each of these choices, it's talking about what happens to the population. The population decreases and approaches a value of 0 rabbits, increases, approaches a value of 40 rabbits, increases, approaches a value of 200 rabbits, and increases without bound. So no calculator on this except where indicated in the problem. So I'm not going to use otherwise I could just graph this and see what the graph looks like to see what's happening when time is greater than 0. So to get a feel for this, to see whether the population is increasing or decreasing, what would happen? What is the population at time 0? At time 0, if I put 0 in for t, I get 0. Okay? So this model says that the population is 0 at the beginning. What about when time is 1 month? When time is 1 month, is it greater than 0 or less than 0? Should be greater than 0. In a realistic situation here, this would give us 200 divided by 6. That is greater than 0, right? So the population appears to be increasing, so not decreasing. Okay, so one of these last 3 choices. Now it's asking us, okay, does it increase without bound? Does it approach a value of 40 or approach a value of 200? They're asking us what is happening as time, I almost put an X there, as time goes to infinity. What is p doing? What is the population doing as time goes to infinity? As time goes to infinity, this 1 on the bottom will be insignificant, so I am ignoring that 1. So this is the same thing as limit as time goes to infinity of 200t divided by 5t. The 2's reduce out, and 5 goes into 20 40 times. So the long-term behavior of this situation will be 40 rabbits. As the population, it will increase until it reaches a value of 40 rabbits, and then it will remain steady. In a realistic situation, the population of rabbits would never go to infinity, right? That would be a bad model if the population is going to infinity as time goes on. The world would be overrun with rabbits. They'd be falling off the planet. Okay. Okay. Number 2. The table gives the cost per ton for a certain type of landscaping stone for orders from 0 to 10 tons. So let's take a look at the table. Between 0 and 2 tons of stone, it would cost $40 per ton. Between 2 and 4, it will cost $39, and so forth. So an order of 5 tons would cost 40 for the first 2 tons. That would be, so an order of 5 tons, just to get a feel, 5 tons, it would be 40 for the first 2 tons, so that would be 40 times 2, because it's 2 tons. 39 each for the 3rd and 4th tons, so 39 times another 2 tons, right? And then $36 times 1 for that 5th ton. So 2 plus 2 plus 1 is the number of tons. It's just divided up into the ranges for the number of tons. If the function c models the cost of an order of x tons, which type of function is the best choice to describe c of x? Piecewise linear, linear, quadratic, quartic. Let's write the function for c here. These are definitely going to give us different pieces. What would happen if you had 1 ton or up to 2 tons? For up to 2 tons, it would be $40 times the number of tons. Then $40 times the number of tons. And that would be if x is between 0 and 2 tons. But if you go above 2 tons, it would be the 80 from the first 2 tons plus 39 times however much you have, but we need to subtract out the 2 that were under this amount. So whatever much you have, let's say you had 3, you wouldn't be multiplying this by 3, you'd be multiplying it by 3 minus the 2 that were over here. And that is if x is between 2 and 4. Okay, so what if we're in between this? Well, then we would have the 80 from the first 2. We would have 39 times the second 2 tons. And then however much we have, minus the 4 that were already used up, and that would be if x is between 4 and 6, and so forth. I can stop there. They didn't ask me to write the function. I could write the function, but clearly it is piecewise linear. Piecewise linear. Okay, next step, number 3. This one is with a calculator. Okay, the first table gives the coordinates of 4 points in the xy plane. The second table gives different function model types and the corresponding predicted value at 2.5 for x. For a best fit function of that type, okay, so this is the cubic model, this is the quadratic model, this is the linear model, and this is the constant model. Okay? Clearly, the constant model is not going to be a good fit. True? The constant model would be y is always the same number, and these are not always the same number. That's not going to be a good fit. I can rule that one out. Okay, the graph of one of the function models in the table passes through all 4 points, so clearly not the constant model. What is the predicted value at x is equal to 2.5 for this function? Okay, so let's do an analysis on this function. So I'm going to pull out my calculator. I'm going to type in these 4 points in for my lists. So stat, edit, I'm going to clear out what's there and insert my new x values. And my new y values. Okay, so according to this, one of these is an exact fit. So one of these should give me a regression r squared value of 1. So let's find out which one. So first I'm going to check, I guess I'll check the cubic first. So stat, calc, cubic is number 6. And I don't have to store it because they've already given me the answer. Okay, calculate. Oh, that was lucky. I found the r squared is 1. So r squared here is 1. So I know that this is going to be my answer. Okay, so let's just, for the sake of doing this, let's go and do the quadratic. Quadratic is number 5. That r squared was 0.898. And the linear, and they tell me which one to use here, ax plus b, that will be number 4. That's a bad r-squared value. So we're using the cubic model, and that cubic model, its value at 2.5 is 9.125. So A. Okay. Number 4. Let's take a look. 100 liters of water. Let me get this straight. Okay. No calculator on this one. It's not indicated in the problem. So 100 liters of water and 5 kilograms of sugar were added to an empty mixing tank to make sugar water. Okay, so 100 liters of water and 5 kilograms of sugar were added to make sugar water. Starting at time 0, additional water is added to the tank at a rate of 10 liters per minute, and additional sugar is added to the tank at a rate of 2 kilograms per minute. Which of the following gives an expression for C of T, the concentration of sugar water in kilograms per liter in the tank at time greater than 0 minutes? The units here are your friend. It's telling you what to do. It's telling you to put kilograms divided by liters, kilograms per liters. I'm starting off with 5 kilograms and 100 liters, kilograms per liter. I'm adding 2 kilograms of sugar per minute. So I'm adding 2 kilograms of sugar per minute. So 2 times the number of minutes. I'm adding 10 liters of water per minute. That's the function. That's the concentration. Okay? A different type of problem, asking you if you understand a situation and how to get a function out of it. Okay, number 5. A music agent is planning a series of concerts at local farms around the nation. The agent is building a model to estimate crowd capacity based on different sizes of square fields. Which type of function is most likely to model crowd capacity in this situation? I need to pause. Okay, sorry about that. My timer downstairs was going off. I had to get something out of the oven. So anyway, okay. So what type of function is most likely to model crowd capacity in this situation? Okay. Linear, piecewise linear, quadratic, or cubic. So they're trying to see which size of field to make for crowd capacity. I saw a couple of problems of kind of vaguely similar to this situation, to this type of problem on AP Classroom. So if they want to know how many people can fit in essentially how many people can fit in a square, would that be linear, piecewise linear, quadratic, or cubic? Okay. Let's just, for the sake of discussion, that first square, let's say that you could fit 9 people in it. How many people would you fit in the next size up? The next size up? Do you agree that that would be 16? The next size up would be 25. These are increasing, these are square numbers. So this will be a quadratic situation. Okay? Number 6. The ancient Pythagoreans studied figurate numbers, which are numbers that can be shown by taking dots or spheres and arranging them into geometric shapes. For example, the square numbers are 1, 4, 9, 16, 25. Those are the square numbers. Those will be modeled by a quadratic. All right? And each of these numbers of dots can be arranged into a square. Yes, they can. We just did that in the above problem, actually. The tetrahedral numbers similarly specify the number of spheres needed to create a tetrahedron. A tetrahedron, which is a triangular-based pyramid. A triangular-based pyramid, so all three sides of this pyramid are triangles. The tetrahedral numbers are 1, 4, 10, etc. Which of the following statements is true? So let's read the statements to see what they're even looking for. The tetrahedral numbers are best modeled by a quadratic function because the second differences are non-zero constants. Are a non-zero constant, sorry. The tetrahedral numbers are best modeled by a quadratic function because the third differences are non-zero constant. I know that that's not true because quadratic would not be a third difference. I also know that A is not true because I know that these are the square numbers. This is not going to be a quadratic, but I'm going to leave it. I'm just going to leave it. The tetrahedral numbers are best modeled by a cubic because the second differences are a non-zero constant. The tetrahedral numbers are best modeled by a cubic because the third differences are a non-zero constant. Already, I'm really leaning to D for this answer. Even without doing a lick of work, I'm leaning towards that because it makes sense. But I'm going to go ahead and find the second and third differences. I'm running out of space already. Let me write a little bit smaller. Okay, there's my numbers. So I'm going to do the first difference. If the first difference is a constant, then this is linear. Okay, so the first difference, I'm adding 3 to get to 4, I'm adding 6 to get to 10, 10 to get to 20, 15 to get to 35, 21 to get to 56, and here I'm adding, what am I adding there? 28. Not a constant, so not linear. That's not one of the choices, but if this was a constant, it would be linear. Okay, next difference. If this is a constant, then these are going to be quadratic. So the first constant, that would be if it was linear. For this one, this would be if it's quadratic. So adding 3, adding 4, adding 5, adding 6, and adding 7. Not quadratic, because this is not a constant. So I do know what my answer is, but just to complete my thought process, this has to be cubic because the third difference is a constant. So D. Okay, I'm going to pause there, start a new video so that this video is not too long.